Hi everybody, I hope this video finds you well. Today we're going to be continuing on with sort of our study of advanced probability. In the last video we sort of introduced this idea of a conditional probability, and in this video we're going to learn a couple basic definitions that are sort of directly connected to this idea of a conditional probability. So we're going to make a couple definitions here and then look at a couple examples to help us understand those definitions. Then in the next video we'll sort of see why it's so important to have these two new definitions and how it sort of directly relates to our last big topic, which is talking about the probability of multiple events. So we're going to be discussing the difference between being independent and dependent. So two events, E and F, are said to be independent if the probability of E is exactly equal to the probability of E given F. Now, this over here is one of those conditional probabilities. This is saying you're calculating the probability of E with the extra information that F is going to happen. So what this is basically saying is that two events are said to be independent if knowing that one of the events, F in this case, doesn't really change the probability of E. That's what this mathematically is saying. It's saying that the probability of E is the same as the probability of E even if we know F is going to happen. In other words, knowing something about F tells us no extra information about E, so we call those two things independent. Being dependent just means that that extra information really is useful. So two events E and F are said to be dependent if the probability of E is different than the probability of E when you know F is going to happen. So you can see why we're doing these definitions after the last video where we introduced the conditional probability. These definitions here are based on those conditional probabilities. So before we get into doing some computation with these, and we will do an example with some computation, let's just get a little bit of sort of an intuitive sense of independent versus dependent with a couple quick examples here. So for each of the sort of following pairs of events, we're going to decide if they're independent or dependent. And we're going to make this decision not doing any sort of calculation, but just by sort of thinking about the situation. So let's take this first one. We roll two six-sided dice. So event E is that the second dice comes up a 6, and event F is that the first dice is a 6. So what you want to sort of imagine here is, does it matter in terms of the second dice coming up as a 6 that you know the first dice is a 6? So imagine you bet all of your money that the second roll is a 6. So obviously that's a sort of risky bet, but you roll the first dice and it comes up a 6. Are you excited? Are you disappointed? Does it not matter? Well, the answer should be that it doesn't matter. That first dice coming up as a 6 has no impact on the second dice being a 6. The dice don't communicate with each other. They don't tell the other dice, hey, I came up as a 6, so you can't, or I came up as a 6, so you have to. There's no relation here. So this would be an example of an independent pair of events. If you, for some reason, knew that the first dice was going to come up as a 6, that tells you nothing extra about the second dice coming up as a 6. It would still be a 1 in 6 chance that the second dice comes up as a 6. As you can imagine, right, generally rolling multiple dice is going to be an example of independent because each dice is sort of separate from the other dice. Did it have to be dice here? Well, no. If we had done that, it had been coins. If this said the second coin is heads and the other one said the first coin is heads, then it would also be independent. So good examples of independent events are multiple rolls of a dice, multiple flips of a coin. All right, let's take a look at this second one. So now, instead of rolling two dice, we're going to draw two cards from a deck. So event E is that the second card that we pull out is an ace, and event F is that the first card is an ace. So again, we're sort of thinking here is, if we know that that first card is an ace, so we pull a card out, look at it, and see that it's an ace, does that change the probability that the next card is an ace? Well, the answer here would be yes. If you bet all your money that the second card you pull out is an ace, you are not thrilled when you see that the first card is an ace. Because if you think about it, there are only 4 aces in the deck, and by knowing that the first one is an ace, you've removed one of those 4 aces. So when you go to pull out that next card, there's only 3 aces left. So you've changed that probability because of that extra information. So this is an example of a dependent pair of events. Generally speaking, anytime you're drawing things or taking things out of a group, those are going to be dependent. So if you think of that, we've done a lot of examples with like taking people from rooms or drawing marbles out of a bag or drawing cards from a deck. Anytime you do multiple draws or multiple selections, that's going to be dependent because once you choose one of those people, one of those cards, or one of those marbles, that person, that marble, that card has been taken out and can't be chosen again. So those are generally dependent situations. All right. Last one, just to show you guys that we have to be very careful when we go to just single events. So here we go. We've got you're rolling a dice. So it's starting to sound like it's independent because we know multiple rolls of a dice are independent. But notice we're only rolling one dice this time. So event E is that the dice comes up a 6. Event F is that the dice is a 5. Well, let's think about this. If you know that this is going to happen, that dice is going to come up as a 5, does that change the probability that the dice is going to come up a 6? Well, yeah, because you're only rolling one dice. So if you know that it's going to come up as a 5, then you know it will not come up as a 6. So knowing this gives you a tremendous amount of extra information because you know the first dice is not going to be a 6. So this would be an example also of a dependent pair. Actually, this is a pair of events that we have another name for. E and F in this case are mutually exclusive. They actually can't happen at the same time because there are about two different things happening on the same roll of the dice. So they're mutually exclusive. And actually, whenever things are mutually exclusive, that immediately implies that they are dependent. So if you guys ever have a mutually exclusive pair of events, you automatically know that they are dependent. The other direction does not hold. We just did an example here that two things were dependent, but certainly not mutually exclusive. It is possible to get the second card to be an ace, even when the first one is an ace. So this is only a one-directional statement. If things are mutually exclusive, you automatically know they're dependent. That's it. So what's the point of doing these sort of three things? Well, these three are trying to help you guys understand intuitively the difference between independent and dependent. You can sort of see that independent things come from multiple iterations of dice or coins or things that are really separate from one another. Whereas dependent comes from doing multiple iterations of things that are related to one another, like drawing cards from the same deck or people from the same room, etc. This last one is just to indicate that we have to be very careful when we're talking about events that relate to the same action, because we only rolled one dice here and we had two events about that. So we're going to study this case just a little bit more in one more example, even though these two cases are really going to be the main ones we use in future videos. But I'd like to do one more example about this and actually show you guys mathematically how to check this definition. So we're going to do one more sort of computational example, and this example will give you guys some additional practice just calculating basic probabilities, since we like to keep stressing that as our main idea here. All right, so for this one, we've got actually some data here. So we're going to suppose that El Camino College is studying its students' ages and their ultimate educational goal. So what they do is they hand out a survey to 360 students, and they get the sort of following data. So they group students into either under 25, 25 to 35, or over 35. So they gave them sort of three age brackets. And they allowed students to say one of four educational goals. They could say that they wanted to get their associates, a bachelor's, a master's, or a PhD as their sort of overall goal. This table right here, we have a name for this. This would be called a two-way table. So before we even get to looking at these questions, we should know we should be probably tacking on all the row and column totals. So let's go ahead and do that. We can get some row totals to start with. So 53, 65, 42, and 17. That's going to be 177. So apparently there are 177 students who are under 25. Then 41, 46, 15, and 3. That's 105. And then 34, 38, 6, and 0. That's 78. So there were 78 students who were over 35. In terms of column totals, we've got 53, 41, and 34. So that's going to be 128. So 128 students who had associates or wanted to get an associate's degree. 65, 46, and 38. 149 students had the goal of getting a bachelor's. 42, 15, and 6. 63 students wanted to get a master's. 17, 3, and 0 is going to be 20 students wanted to get a PhD. All right, now we can add up those row totals or those column totals. Either way, we should get 360. Keep in mind, we actually knew that it was going to be 360 because they said that they gave out the survey to 360 students. All right, so for the rest of this, we're going to be doing some probabilities. And notice at the end, we're going to ask ourselves a question about independent or dependent and actually get to sort of do that definition. So let's calculate some probabilities here. So we select a student, so just one student from the survey at random. Let's calculate the probability that the student wants to get a bachelor's. Well, we're choosing this student from this survey. So there are going to be 360 students that we can choose from. How many of them will have this trait that we want? Well, we want them to want to get a bachelor's. So that'll be that 149. So this probability would be 149 out of 360. Now, we're doing this as a probability, but this should feel identical to what we did back in the conditional analysis section. If we took the extra time to just write this as a percentage, this would be the same as the percentage of students in our survey who wanted to get a bachelor's. So we're just doing the same thing we've already done, but from a probability perspective. All right, let's get the probability that the student we pick is over 35 years old. Well, we're picking them out of the survey, so it's going to be out of 360. How many of the students had this trait of being over 35? Well, right there, it was 78. So 78 out of 360. All right, we want the student to either want to get a master's or PhD. We see that the or is going to be addition. So for masters, we can see that there were 63 of those. So 63 over 360 plus for PhD, we can see that there were 20 of those. So 20 over 360. Do we have to be worried about any overlap? Do we have to subtract anything here? Well, master's and PhD can't happen at the same time because they're a goal. You can only have one ultimate goal there. So there is no overlap. In other words, these two are mutually exclusive. So we don't need to worry about any overlap. We just add them up. We get 83 out of 360. All right. Let's try this one. We want the student who wants to either get an associate's or is under 25. So associates, well, that would be that 128 there. So we take 128 out of 360, and we're going to add to that the people who were under 25. So that was 177. But we do need to consider, were there any people who were double counted? In other words, was there any overlap between an associates and under 25? Well, associates was this way, under 25 was this way. That means the overlap was at 53. So we need to subtract 53 out of 360. Putting all that together, 128 plus 177 minus 53, looks like we should get 252 out of 360. All right, now we've got a couple ands in here. So we want to get that the student is 25 to 35 and wants to get a master's. So 25 to 35 and wants to get a master's. We just intersect those two things. Looks like that would be 15. So that would be 15 out of 360. All right. We've got another and here. So they need to have both these traits. They need to be over 35 and want to get a PhD. So over 35 and PhD. Well, we notice that we'd actually get 0 there. That would be 0 out of 360, which is 0. This would actually tell us that these two things, being over 35 and wanting to get a PhD, at least according to our data, are mutually exclusive. It is, at least according to our survey, it's impossible to pick somebody out of this survey who is both over 35 and had the goal of wanting to get a PhD. All right, all of these here were just basic probabilities, just to give you guys a little bit more practice with that. Now, we've got a couple probabilities that have these conditionals on here. So we have this extra information. So the first one is we want the student to want to get a bachelor's, and we have the extra information that they are 25 to 35 years old. So we know they are 25 to 35. So we know they're in this group here. That means they are one out of those 105 people. So the denominator here is going to be 105. Instead of 360, because we're not from the overall survey, we know that they are 25 to 35. How many of those people wanted to get a bachelor's? Well, in that 25 to 35, That's that row right there. Bachelor's would be right there. So it would be that 46 out of 105. So the probability that the student would want to get a bachelor's, if we know they are 25 to 35 years old, would be 46 out of 105. All right, same thing. Now we want to get the probability that they are under 25, but we know they want to get a PhD. So we have the information that they want to get a PhD, so they must be somewhere in this column. That means they are out of that 20 total people who wanted to get a PhD. So we're in this column. How many of those people in that column were under 25? Well, 17 of them. So it would be 17 out of 20. So notice that in these ones where you have a conditional, the denominator changes because you have extra information. Originally, we were always out of 360 because there were 360 students in the survey. But when we had extra information, those denominators changed. All right. Last thing to sort of talk about, which is going to be the new concept, is we want to try to understand, is being over 35 and wanting to get an associate's degree independent or dependent? Now, we can't answer this intuitively. We can't say, oh, it's independent because it's like a dice or a coin, and we can't say it's dependent because it's like choosing multiple people out of a room because we're only taking one person. So we need to actually study this from the perspective of the definition. So what we need to do is we need to do a comparison. Let's see if the probability of being over 35, if that is equal to the probability of being over 35, given they want an associate's degree. So in other words, what we're going to do is we're going to check, is the probability the same of being over 35 if they're just chosen at random from the study, or if we know that they chose to, or they want to get an associate's. So let's check this left-hand side. Well, what's the probability that somebody is over 35? This has no extra information, so it's going to be out of 360. It would be 78 out of that 360. So over here, we'd have 78 out of 360. And we're asking ourselves, is that the same as being over 35, given that they wanted an associate's? So we know that they want an associate's here, so we're in this column. That means it's going to be out of 128. So this was going to be something out of 128. How many of those 128 people were over 35? Well, there were 34 of them. So it would be 34 over 128. Now, you might look at these and say, well, those are different. Those are different numbers. You got to be very careful, though. These are fractions, and as you guys know, sometimes fractions that look different can be the same, like 3 over 6 is the same as 2 over 4 is the same as 1 over 2. So let's convert these into decimals to just make sure. The left-hand side, 78 divided by 360, you should get on the left-hand side there 0.217. And on the other side, 34 divided by 128, you should get 0.266 about. And you can see that those two things are not the same. So, since these are not the same, we would say that this is dependent. So, all right, let me rephrase that just a little bit, just to make it a little clearer there. So this would mean that over 35 and is wanting associates are dependent. If these two things had come out as equal to one another, then we would say that they are independent. What does this actually mean here? Well, this means that on this left-hand side, if we just were going to pick somebody out of the survey at random, we'd say that there's about a 22% chance, 21.7, that they're over 35. So you can sort of imagine maybe all 360 people are standing in a room somewhere, and if you go and you pick a random person, the chance that they're over 35 is about 22%. However, if you start to talk to them and they tell you that they want to get an associate's degree, you would change the probability that they're over 35. Instead of thinking that it's 22% about, you would start to think that it's about 26 or 27%. In other words, they're a little bit more likely to be over 35 because of the extra information that they wanted to get an associate's. So this is in a lot of ways doing exactly what you guys did back in the conditional analysis section. But it also more formally is checking the definition of dependent versus independent. Like I said, most of the time we're going to do independent versus dependent sort of intuitively because we sort of know multiple rolls of a dice or multiple flips of a coin are independent. multiple draws from a deck or multiple selections from a group are dependent. But this was just a chance for you guys to see exactly what that definition actually meant.